Hello guys, today we're gonna discuss about Gauss's law and its application. So first we have to look into what is Gauss's law. So Gauss's law states that the flux through any surface enclosing a charge Q is Q by epsilon zero. So the flux, what is the flux? Flux can be written as integral of E dot dA. E is the electric field and E dot dA gives the total number of field lines to the surface. If there is a surface A, S, and from doing E dot dA, we got total number of field lines to that surface. Or so the closed integral of E dot dA will gives the flux. Can be explained as the total number of field lines to the surface. So according to Gauss's law, the flux is equal to the charge enclosed by the surface divided by epsilon zero. So Q enclosed is the total charge to the surface and the flux is equal to the total charge enclosed by the surface divided by epsilon zero. This is the Gauss law. So next we have to look into the applications of Gauss's law. So Gauss's law helps us to find the electric field due to a uniform charged solid sphere, an infinite plane of uniform charge density, two infinite parallel planes with equal and opposite charge density. Using Gauss's law, we can find the electric fields of these things. So, not over explaining here, I'm just going to solve some problems to find the electric field due to different space planes as told here. So let's move to the first question, and here we have to find the electric field outside a uniformly charged solid sphere of radius r and total charge q. So here we have the solid sphere of radius r, and we have to find the electric field due to the sphere outside the sphere. So in order to do that, we first need a Gaussian surface. So we have to draw an Gaussian surface enclosing this charge. So we introduce you another sphere. This is a sphere which enclosing this surface. So this has another radius. Its radius is r. So this r is greater than r, our capital R. So this enclose this surface, and this is our Gaussian surface. This is our Gaussian surface. So we have to apply what our Gauss's law into this surface, and we get that is Gauss's law, closed integral of E dot dA is equal to Q enclosed by epsilon zero. So we know this Q enclosed is the charge of the sphere, which is equal to Q as per the question, and this closed integral of E dot dA. Let's find this closed integral of E dot dA. This E can be taken outside as a constant, and it's possible to drop this dot side and make it into multiple, because this E is always parallel. This is E always radially outwards to this surface. So we can take this E as a constant because E has a constant value all over the sphere, and it's always radially outwards to the sphere. So we can take this E outwards of the integral and into integral of A. We can write this as this. We can so integral of the surface dA will give the total surface area of the sphere, which is equal to E into 4 pi r square, which is the area of the surface area of the sphere. So we can substitute this to this equation, and we will get the integral of E dot dA, which is equal to E into 4 pi r square, which is equal to Q enclosed. Q enclosed is equal to Q, the charge of the sphere, divided by epsilon zero. On solving this, we will get E, the electric field outside the sphere due to the sphere, which is equal to E is equal to we can write this just like our Coulomb's law, and we will get 1 by 4 pi epsilon 0 into q by r square into r cap. This is the electric field due to the sphere outside that sphere. So this is the electric field, and we can see that this is just the electric field for electric field due to a point charge as per Coulomb's law. So we can see that this whole sphere act like a point charge when we consider the electric field outside the sphere. So next question, we have to find the electric field due to this plane. So it's an infinite plane carrying a uniform surface charge sigma. Find its electric field. We have to find the electric field due to this plane, uniformly charged plane. So in order to do that, we have to make a Gaussian surface. So here I am taking a Gaussian surface here. So okay, okay, we have to take a Gaussian surface, and yeah, this okay. Consider this as a Gaussian surface in this field. This is a Gaussian surface, and yeah, this is a Gaussian surface, and according to Gaussian's law, this is a Gaussian pillbox. This is a Gaussian surface, and this is the Gaussian pillbox. Gaussian pillbox of area A. This has a area A, and this we have to apply Gaussian's law to this surface, and we get what integral cos integral of E dot dA is equal to Q enclosed by epsilon 0. So we know that this Q enclosed is equal to this surface of uniform charge sigma. So this Q enclosed is equal to the area of this pillbox, lid of this pillbox into sigma. The uniform charge density into the area of this pillbox, we will get the charge enclosed by this pillbox. So Q enclosed is equal to area of the lid of this pillbox A into sigma. Let's now consider this integral E dot dA. On considering this integral E dot dA, we know that it can be taken outside as a constant because uh, he has a constant value all over the surface, and it's uh, also points parallel to the surface area component dA. Okay, surface component dA. So we can drop this dot sign and take this E as a constant. On integrating dA, we have to consider the two surfaces, the bottom surface and the upper surface. Okay, top surface and the upper surface, and we have to consider the top and bottom area. So we will get E into 2a integral dA. We will get E into 2a. This is equal to cos integral of E dot dA. We get E into dA, and we can substitute this to this equation, and we will get closed integral of E into 2a is equal to Q enclosed by epsilon 0. So from here we can which is equal to Q enclosed, we know, into sigma A into epsilon 0. From here we can find the electric field E is equal to this A and this A cancels, and we get sigma by 2 epsilon into n cap. N cap is the area. N cap is the component parallel to n cap is the component parallel to perpendicular pointing away from the surface. N cap is a component, unit vector pointing away from the surface. So this is the electric field due to a infinite plane carrying uniform charge sigma. So Looking into this equation, we know that there is no 1 by r square or 1 by r term in this equation, because no matter how far we go from the surface, there will be no decrease in the electric field due to this plane carrying charge, because the further we move away from the plane, the more and more charges will come into our field of view. So no matter how far we go, there will be no decrease in this electric field. As the as per Coulomb's law, there is no 1 by r square or 1 by r term uh, in this equation for electric field that we should consider. And that's all for infinite plane carrying a uniform surface charge sigma. So now we have to consider two planes carrying uniform charge sigma, opposite charges sigma, positive sigma minus. So two infinite, infinite parallel planes carrying equal but opposite uniform charge density plus or minus sigma. Find the field in each of three regions. One to the left of both, between them, to the right of both. So we have three regions and we have to find the electric field in these three regions. So we have to just draw this electric fields. Yeah, I'm just drawing these things, and these are the two parallel planes carrying uniform charges sigma, uniform charge sigma of sigma positive and sigma negative. So this has charge sigma positive, this has charge sigma negative. So this is a positively charged plane. So the electric field will be moved away. There will be electric field away from this uniformly charged plane. So there will be electric field away from this plane. E positive, these are electric field that are rising from this positively charged plane. And this is a negatively charged plane, and there will be electric field into this plane. So E negative due to this negatively charged plane, and also here, also in this plane, into this negatively charged plane. So now we have to consider this two, one, two, three regions. So here we can see that there are electric fields in these three regions due to this plane. So here these electric fields are opposite to each other. So electric field cancels each other. And here also we can see the electric fields are opposite to each other. And so the electric field cancel each other. So in region 1 and 3, there will be no electric fields. There is zero electric field, and in between them we can see the electric fields are in the same direction, so they conspire each other, and we will have a effective electric field of so we know that due to a infinite parallel plane of uniform charge density sigma, the electric field E will be equal to sigma into 2 epsilon 0. So here will be E positive and E minus in the same direction, so they will adds up, and we will get an effective electric field of we will get an effective electric field sigma by epsilon 0. So at the center we have an electric field in this region 2, we will have an electric field sigma by epsilon 0 in the right direction, to right direction. Elsewhere the electric field is 0. So this is the Gauss's law and its applications. So, thank you for listening. Bye bye.